Good afternoon. My name is Bill Kramer. I'm the director of the Blue Waters Project at the University of Illinois, Urbana-Champaign, and at NCSA. So I'm going to talk a little bit about how we're using Synexion devices and what the science teams are using those for to have high impact for science that is at unprecedented scale. So I'll spend about 20 minutes to bring you up to speed on what we've been doing and how things work and how our things are being used. So Blue Waters is the sustained petaflop data and computational system funded by the National Science Foundation. Sometimes it's called the Track 1 system because it's at the high end of the pyramid. And we've been in service for about a year and a half. 6 months of early operations and then a year of full service. So some of the things I'll report is the first time people have been actually being able to show impact and accomplishment over the first year of the system's life. It's a collaboration between us, NSF, the state of Illinois, Cray, Seagate, and a variety of others. So first, a word about NCSA. We're a leader in deploying high-performance computing and data systems. We have about a 30-year history of doing this for the National Science Foundation predominantly, but also for some other organizations. And obviously Blue Waters is the biggest system we have at the moment, but we also have about 250 computing experts, researchers, as well as professional staff doing a wide variety of projects in data. Projects that include the National Data Service, which is an umbrella of being able to do discovery and sharing of data across many repositories. The Brown Dog Project, which is another way of trying to figure out how to automate the annotation of data that may not be structured. And working with industry, we have a large set of industry partners, and a lot of that is surrounding data as well. And obviously, we can leverage all the resources and intellectual power of the university, which is one of the top-tier technical universities. We also are the leader of the NSF Exceed project, so Blue Waters and Exceed are the two biggest, largest funded projects. Exceed is trying to put together a set of software and services around all the other resources throughout the NSF academic spheres, and that's led by my colleague John Towns. So we'll talk about Blue Waters. The goals of Blue Waters have been out for quite some time. The first one is sustained performance. So we only concentrate on time to solution, and that's the main driving factor. That's one of the reasons why, for example, Blue Waters is not listed on the top 500 list. That was a very conscious decision because we don't think that that relates to sustained performance. So I'll give you some examples of how we speeded up time to insight, both with the very large-scale machine, but then doing other things such as workflow improvements to actually let what is simulated or modeled on the machine or analyzed then be able to be used much quicker than it was before. So we help the science teams make use of the sustained performance of the machine. We've been working with some science teams for 2 or 3 years. Turns out when we do surveys of their code and where the bottlenecks are, one of the big areas is how I/O is handled, and we've had to work with maybe a quarter of our teams to try to improve how their codes are doing I/O, because that becomes the biggest bottleneck to scaling, and that's why we wanted a very robust system. The other thing is because we don't know what science will be approved to use Blue Waters. It's not predetermined. It rolls over, and there's an allocation process every 6 months. We have to be ready to do any type of thing, which means we need a very well-balanced system, very robust system, that we are able to deploy the resources in a flexible manner. And then obviously that takes understanding how you operate at such scale. Blue Waters is 50% bigger than any other system Cray had ever built in terms of computational work. So here is Blue Waters. The unique aspects is not only its size, 288 racks, 28,000 nodes. The equivalent, if you count things in cores, is about 800,000 cores. But this is the thing that we'll concentrate on for the rest of the talk. We have Synexion units, which are manufactured with Seagate or by Seagate, and this makes Blue Water is the most computationally and data intensive system in the world. The combination of the bandwidth, the capacity, and then our nearline storage, which is the world's biggest HPSS system, all playing together to enhance the ability for people to do science. And then obviously the memory, there is no other system with that much memory in the world. Indeed, we do have times where we're using around 1.2, 1.3 petabytes in aggregate across the system. So it actually gets used in addition to being a unique resource. And then we're connected to the outside world. This says 120 gigabits. That's what we have today. In a couple months, it'll be about 450 gigabits. So we are never the bottleneck for people moving data to us. We match the backbone speeds of almost all the major research and engineering networks in the United States. And because we connect into Chicago, then that goes worldwide in terms of all the other research connections. So the robustness, there is no other system that has 450 gigabits of bandwidth connectivity there. So the internals of our system looks like this. Yeah, because this system is named Blue Waters, we have other things that are kind of in the water theme, like our data subsystems are called SCUBA. There's some acronym for that. Our small test system is called JYC for Jacques Cousteau. We have other things like that we have fun with. But we have a hybrid machine that includes about 22,000 nodes of x86 processors, 32 cores per node. And then we have one of the world's largest GPU clusters by using the XK7 nodes. And they're used by different teams. Sometimes they're used by the same team doing different phases of their calculation. Come out with an InfiniBand fabric to the Seagate devices. We have 36 racks of cluster store 1600 in 3 file systems. Home, Project, and Scratch. So Home and Project are about 2.1 petabytes each, and then Scratch is about 21 petabytes each. And Scratch is where most of the I/O work is going on with that there. These are great devices for us because not only are they very efficient and robust, but they also take up very minimum floor space. To get a terabyte or I'm sorry, petabyte plus into a rack, it's really good. We have about almost 100 I/O servers. They're broken up a couple different ways, obviously logging in, compiling, but the 2 big ones are our import-export nodes. We have 50 of those nodes. That's where the data transfer takes place to the outside world, to our HPSS system, and the online storage system. The other places call those data transfer nodes. They're robust systems. And then we have the HPSS data movers that manage all the tape drives. We have 255 tape drives at the moment connected to about 28 movers. And that's how the data flows through those servers, either to the nearline storage system, the online storage system, and the outside world. And then obviously the online storage system also is visible by all the compute nodes through our 580 something LNet routers. This is the interconnect process, the InfiniBand for the Seagate storage, and then our servers for HPSS and how we go out to the outside world. So it's at the time we deployed it, I believe it was the largest 40 gig networking configuration at the time. I don't know if others have gotten bigger than that. So I mentioned that we have to run a diverse workload. Here is a list. It's a little bit old, but of the areas of science and engineering that we were covering. I'll show you a different chart as well. The number of teams in those areas and the application. So it turns out that almost every team uses more than one application at scale. So it's not that you can map and just say, I have 30 teams. We have about 35 major science teams coming from the NSF. They get allocated 80% of the system. Then we're about 150. So we have over 100 other teams using the rest of the research allocation. And the other one is that you can see a distribution of the types of methods they use and where their bottlenecks or challenges are in those allocation or algorithmic methods. So that's where the diversity comes in. This was Tuesday morning, I just went to the site and pulled up our bluewaters.ncsa.illinois.edu and looked, and this just happened to be running. So this is nothing special, but this partition here is using 340,000 cores. It ran for 24 hours, and most of our jobs are 24-hour jobs. There, but you see then also we have other things that are substantial in terms of the percentage of nodes. So that's our common business day. It's not special. It's not once of a time. It's not because we were here Monday at the show and somebody wants to make a big impression. That's the way Blue Waters works in the scale of what people are using it for. So one of those success stories, and I should say, we're very happy to have our first year report, which has about 70 science projects and their success stories. I'll highlight one or two. Is the Computational Microscope. It's a really cool project. Their first solution was 100 nanosecond simulation of the HIV capsid, this unit here. It was 64 million atoms, bigger than was ever done before, so it was best of breed. And that was about 10 times more resolution than they were able to do in any experimental or previous work. And it uses the NAMD code and VMD. So with this, they now are able to target locations on the virus capsid. The virus capsid is injected into the cell. About an hour later, the capsid falls apart, the DNA material is exposed, and that's how the infection takes place. Turns out that changing the timing of that breakup of the capsid has a great impact on the infection rates. So if they can make it go earlier or make it go later, they can change the infection rates for HIV. They also, for the first time, have done an entire chromophore, how photosynthesis works at the electron level, molecular dynamics, and how proteins are made. So those are the three projects this group has been doing. Here's another project. You saw that about 5 of our teams are doing astrophysics. This one has to do with the internals of stars and what happens when one explodes. It has multi-scale, multi-physics. Turbulence is a main part of this activity, fluid dynamics, but this was a visualization at unprecedented scale. This actually was done on Blue Waters itself, not taking the data someplace else, because what we have found is moving data is very expensive for science teams. So we try to keep the data on the machine, and if they have to do post-processing or visualization, they use the XK nodes or something like that. Very high resolution, and by keeping the data and doing the visualization, we had to do software work for that in terms of the driver work on the XKs, rather than 15 days for them to understand what they had just run. They do it now in 24 hours. So that speeds up time to insight, right? So it's not just that one big job and how long that runs and whatever the peak is. It's really the workflow that you have to also work on, because if it takes 4 or 5 months for somebody to analyze what they did, that's not going to be very fruitful for them gaining a lot of improvement. This is a cool one, and this uses about a petabyte of data on a regular basis. And I learned not too long ago, they save only 1 out of 1,000 time steps. So, and that's because of the space it takes. So they would like to save every time step. And we have a visualization activity that is going to take this and some other teams and put it into IMAX theaters and whatever. They need to have 1,000 frames at high resolution. So they're out of 186,000 time steps that they've run, they've only saved 186 of those for their science purposes. So we at least have to go up to a factor of 5 just to be able to do high quality resolution for the public. And as I said, that's about a total of a terabyte of space weather. And the neat thing is they have to simulate the sun, then they have to go 93,000 miles, and then it comes down to interaction with our atmosphere at the nanometer level. So very, very complicated multi-scale codes. Another one about plasma physics and lasers. And this is another interesting example. This comes from Tom Jordan, who does earthquake studies, but it's a really good way to think about how science is done today. So no matter where you enter this spiral, you're going to circle around and get bigger and bigger. So you enter either by looking at data and coming up with some type of model or theory, or you have a model and then you start to simulate. But everybody, all these science teams no longer just compute. They all have to validate their results, and it's no longer sufficient to validate their results just by looking at somebody else's paper and say, yeah, this curve, looks like that other curve or something like that. You have to have quantitative validation. You have to simulate the observed data, bring it back around for verification and simulate in the circle. That HIV example I used, they need experimental data for the electron microscope data and also crystallography data to create the structure that then they use to simulate. And that takes a light source, like an accelerator, to produce the crystallography. So this is the way science is being done today. Tighter and tighter integration with lots of data and lots of computation and simulation. In Tom's case, this was one of his previous simulations. He studies the earthquakes in the LA region, and this is the latest one he's done on blue waters. And what you can see is much more detail, and these reddish areas don't show up here at all, but those are the areas where, on this scenario that they did for an earthquake, they simulate, and 90% of their CPU time is simulating the fracture in the earth in 3 dimensions. 10% of their time is spent trying to understand the results of that, the wave analysis for the infrastructure, homes, businesses, whatever. And the folks at OSC are giving presentations on that. It's really cool because the resolution has to do with how the buildings and how they're affected. But now they can concentrate on those 2 areas, which they couldn't before because there was no data indicating those are the areas more at risk. And to do that post-processing, they have to run 100 million jobs. So again, first time through for this one, they took that data elsewhere, tried to understand it and do 100 million jobs. That took them about 5-6 months before they had any insight. This one we did in a couple of weeks because they ran on blue waters, both phases of what they're doing, and that way the data didn't have to move. So the speed ups are here. They got 4.5 times quicker to insight by doing both their workflows, and we had to work with them to accommodate their customized workflow that they use for that. So what is the data? I mentioned that we've tested it with your help at above 100 terabyte or 1 terabyte per second. These are some of the other characteristics that we have in terms of what the system normally performs at. And this chart is, you can see over a fair amount of time, 6 months time, and we're not always using all these characteristics at the same time, but we do show that in various campaigns and runs and applications, both on reads and writes, we are making use of that capacity in order to accelerate the science that we're talking about. So this is our scratch file system over an extended period of time. Here's data transfer rates, again to scratch. It's the most heavily used, and going up to 6 petabytes a day, but regularly well above 3 or 4 on reads and writes. And that's just observing the traffic about how people are using the system. So yes, the high performance I/O is critical to people being able to make use of systems at scale for science. And it's not just, I'm going to write out my big checkpoints. That's not the way people work. Other thing, scratch metadata rates. Again, this is all observed, and our collection software needed to get adjusted there, so we lost some data. But again, from January through August, and if you look over here for opens and closes, we're running between 100 million and 10 billion opens and closes per day. So again, pretty high numbers for what people think of file systems being able to do, and it's the technology that Seagate produces in hardware and software that allow us to do this. Today's use on, or this was Monday's summary. I just looked at some of the larger teams what they're doing in science, and you can see cosmology, tornadoes, the space weather, management of satellite systems. That's an optimization problem for viewing water resources on Earth, and how the satellites get positioned, protein universe. But here's their snapshot of the storage they had on Monday. The number of files, 17 million, almost 5 million, and we see a range of file sizes. So one of the surprising things is we thought we'd have fewer larger files. We have 10 times more files than we projected when we were designing the system. We're using as much data, but it's in smaller files. And that has to do with the workflows of users, and that's why the metadata operations are so critical for us to be able to have that robustness. We also have been working with the teams to look to the future. So these are some general trends. We have a lot of detail about what types and sizes and methods that we use across all of our teams. We did a study with them earlier this year. But if I were to summarize what the future of at-scale science has, these are the characteristics to come up with. Increased fidelity, that means either higher resolutions, more particles, things like that, more physics, increased fidelity of the simulations. That's what we've been doing. But some of the other ones are, turns out longer simulation times are needed. So just at the same resolution, that space weather example, they do about 2 hours, 1.5 to 2 hours. They can simulate within 100 million, within about 10 million node hour allocation. But the actual event is about 36 hours. So what they really want to do is simulate the entire event. And they can't do that today. It's not tractable. Increase the number of problems. So as we get these best of breed problems, the HIV problem, now there are more teams saying, oh, I have a molecule or an event that I want to study. Now that you can do it at that scale, I have many more problems. We expect probably 20 to 40 teams now have problems that would be at that same scale. It's been proven now the software works that way, and now we have teams coming and saying, I want to do a problem as well. Integration with data sources, 2 ways. That spiral I mentioned means that there has to be much tighter integration with data sources, be they telescopes or whatever, or instruments like light sources or electron microscopes. MRIs, we have some really cool projects that are starting up with MRI data and studying epilepsy. But the other thing is now we're seeing the data products are actually becoming useful in their own right. So it's not just a restart file. They're being shared by the simulation teams to others to make use of as derivative projects. And then the workflows I mentioned have become, we realize they've become a much more important part of shortening the time to insight, because they're typically not been looked at for optimizing or improving. They typically grow out of a variety of people's use of tools and plugging tools together. Genomics is a big area of that. So those have to get looked at, and obviously changing methods for new technologies like many core processors. And then we have this whole area of big data, right? So big data this is all independent of big data and whatever that means. But the way I think of big data is we have processed semi-structured data, stuff coming out of the simulations, may or may not be documented, even payroll, other things. Computers have been doing that. We've been doing that for a long time with devices that, like the ones you make, Seagate makes. Structured observational data, large telescopes, large colliders, accelerators. Those typically take a decade of planning how to organize the data, and it's very well managed, very well thought through about how to optimize the use of the data, what they keep, what they don't. And then we have this, what I call unstructured observational data, anywhere from Twitter feeds, email feeds, social networking things. This is where we don't yet know how to do this very, very well at scale. But these two we've been doing for a long time. So big data is not new in terms of how it relates to big computation, but we have to accommodate new types of uses. So that's the story about Blue Waters in about 20 minutes. And I'm happy to answer any questions or talk any more about it. And we're very proud of what we've been able to do with Blue Waters. But I also know that everybody's busy and needs to go other places. So with that, thank you very much for your attention. Are there any questions? No? how does the file system perform when it's writing large files? It performs very well if, the thing on the file system also you have to realize is that almost all that data is being sent through the interconnect network on the Cray system before it hits the file system. So if it's organized well and there's some locality, it operates very well and very consistently. But there can be crosstalk within the torus, and that impacts messaging like MPI as well as I/O. We actually have probably better command and understanding of controlling the MPI traffic to make it more efficient. The I/O traffic is not they're not the tools to organize where the I/O traffic is going to and where you're placed in the torus to do computing. We spent in other projects a lot of time with topology awareness for computation. Now we have to start doing that for where the I/O is placed or going to in the storage system. So writing out is actually pretty good because it goes to near local LNets, but reading back, you don't know where the data is versus where your job is running. But those rates are real rates using the entire system, and we can replicate those in terms of a terabyte a second. But it uses almost all the compute nodes to drive that traffic. So it's good.
So what you've learned over the last year and a half of operational time, is that you've had a lot of cases where your I/O got with a faster file system help boost the compute?
I would say at the moment faster is good, but not as critical. I think consistency is at least as important in getting to that consistency. Some is the traffic in the high-speed network. Some is what might happen with somebody else using something. Another, though, is being able to manage, for example, where the data lands and getting OSTs filled up and keeping that distributed. And right now, that's not an easy thing to do. Right. So as things start to get filled, when they get to 85, 90% full, then we do see slowdowns for that traffic going to that OST. What we like to do is have thresholds lower than that and redistribute that automatically, and that's challenging to do even to know they're starting to fill up. So those types of things I think are more important at the moment than that consistency and failover operations. So you can bound the time rather than having widely varying times with that. That's what is because we will have reports from the users saying, "Oh, I saw it in this time period of 35 minutes where my time steps got 3 times longer," and that's very painful for them and for us. So I would like to see a lot of attention spent on making things consistent and not having the interference both at the file system and then in the interconnect as much as a faster file system. We do think that we can easily use more capacity and leave things on longer. Improvements in terms of knowing even down to the individual storage units what they're doing is important too, so you can optimize them.
Yeah, and the reason I ask is that I remember that this machine, it's a very balanced machine for storage.
Right. So we'll probably we'll see the need for more storage data as things get more used and more people are there. But right now, consistency is our biggest challenge.